Circular motion, exercise question 27, from H.C. Verma. Here is the setup. We have a top-down view of a cylindrical room of radius r. A block of mass m moves along the inner wall. The floor is perfectly smooth, so there is no friction from the floor. But the wall exerts a normal force n pointing inward, providing the centripetal force. Since the block slides against the rough wall, a friction force F acts tangentially, opposing the motion. The velocity v is tangential to the circle. Watch how the block gradually slows down as friction removes its kinetic energy. The question. A block of mass m moves on a horizontal circle against the wall of a cylindrical room of radius r. The floor is smooth, but the friction coefficient between the wall and the block is mu. The block is given an initial speed v0. As a function of speed v, find, part A, the normal force by the wall on the block. Part B, the frictional force by the wall. Part C, the tangential acceleration of the block. And part D, integrate the tangential acceleration to find the speed of the block after one full revolution. The key concepts. The block moves in a circle, so it needs a centripetal force equal to mv squared over r. This centripetal force is provided by the normal reaction N from the wall. Now here is the interesting part. The kinetic friction depends on N. But N itself depends on the speed of the block. So friction is velocity dependent. Friction equals mu times N, which is mu mv squared over r. As the block slows down, the normal force decreases, which means friction also decreases. This coupling leads to an exponential decay of speed, a beautiful result. Part A. The block moves in a circle of radius r. The wall pushes the block inward, providing the centripetal force. So the normal force N equals mv squared over r. Part B. The frictional force is kinetic friction acting tangentially, opposing the block's motion. It equals mu times N. Substituting N from part A, we get F equals mu mv squared over r. Part C. The tangential acceleration is caused by friction, which decelerates the block. So At equals minus F over m, that gives us At equals minus mu v squared over r. The negative sign indicates the block is slowing down. Part D. We need to integrate the tangential acceleration to find speed after one revolution. Using the chain rule, At equals dv dt, which can be written as v times dv ds, where s is the distance along the circular path. Setting this equal to minus mu v squared over r, we cancel one v from both sides. This gives dv over v equals minus mu over r times ds. Now we integrate the left side from v0 to v, and the right side from 0 to s. We get natural log of v over v0 equals minus mu s over r. For one full revolution, the distance along the circle is s equals to pi r. Substituting, natural log of v over v0 equals minus mu times 2 pi r over r. The r cancels beautifully, giving us ln v over v0 equals minus 2 pi mu. Exponentiating both sides, we get the final result. V equals v0 times e to the power minus 2 pi mu. A clean exponential decay. Here are all four answers. Part A, the normal force is N equals mv squared over r. Part B, friction force is mu mv squared over r. Part C, tangential acceleration is minus mu v squared over r. And part D, the speed after one complete revolution is v0 times e to the minus 2 pi mu. Notice how the radius r cancels in the final answer. The speed after one revolution depends only on the initial speed and the friction coefficient. Exam tips. First, this problem features velocity-dependent friction. When the normal force depends on velocity, as in circular motion against a wall, friction also depends on velocity. This creates nonlinear deceleration. Second, remember the integration trick. dvdt equals v times dv ds. This converts the time derivative into a distance derivative, which is very useful when friction depends on speed rather than time. Third, the result is an exponential decay. The speed v equals v0 times e to the minus 2 pi mu. This means the block theoretically never fully stops. Also notice that r cancels out in the final answer. The speed after one revolution depends only on v0 and mu. Like and subscribe for more circular motion solutions at MAGPIEHUB.